All right, jumping back into where we're at on the screw conveyor. Working on this inlet end. So what I have pulled up here is just last time we were together, we created a couple more assemblies. We had our original housing. We've created this assembly now. It's the screw. And then we created one where we combine the housing and the screw together. So I'm going to open up both of these. I don't need this specific housing assembly open, but I opened up both of these two assemblies that we started. So I have those open. There's my screw assembly where we left off. And there's how it fits in the housing. So now we're going to just get nitpicky here with this, how the shaft works when we just left off. So what I noticed is, and I went ahead and opened that part, is when we assembled it, the right part, surface. So when we built it the other day, what I noticed is like, yep, there's a 2-inch shaft. I'm kind of following my standard manual, and so these are sizes that I selected based off my manual. The 2-inch pipe size for the center pipe and a 2-inch solid shaft. And just as I built that in here, I was like, and our other dimensions that we follow to get it how it fits. But once I did it, I was like, well, my OD doesn't match my ID. And so this is one change I'm going to make. And I have a couple options. I could look at a different pipe's schedule thickness and see if one's available that would help fill this void between the two. Um, I could do a half section. So I'm just looking to take care of this issue where if I buy a 2-inch solid shaft, it actually doesn't fit into a schedule 42-inch pipe. Very tight here. It's got quite a bit of tolerance here. And I can do a quick check on how much it really has. But it's gonna my end shaft's gonna be a machine part. So I would rather start with a bigger end shaft than I move down to fit this circumstance. That's the way I'm going to proceed. What if I was evaluating these, how different they are. I just need to know this measurement, this input 6.7. Just like this is 2.0. So then my shaft it's 2 inch. So really, I have 16th of an inch is 0.0625. And so I'm over a 16th of an inch of clearance all the way around. Well, difference in diameter. So if I think about how much clearance is that all the way around, it's 2%. I just divide this by 2 and get a look at what that is. So it's really, 33 and a half thousandths clearance around there. And that might be too sloppy for a machine. And I mean, there's things I have to consider here though as well. It's that when the pipe is produced, there's an inner seam, and so there is some working that has to go into the end of the pipe to make things fit. Like they're not just like sometimes the ID of a pipe, while it's structurally sound, can have ridges and bumps in it that are having to be addressed by a machinist in order to slip something into it. They do make seamless pipe, it's more expensive, but it might be for receiving type applications like this that have slide stuff into it. So I think the inner board and truly, I mean, they do make expensive pipe for those reasons. In this case, where I only have to insert it, less than 6 inches, I think it's 4 and 3/4 into my grade. That can kind of be addressed from the outside by the machinist or another technician to make it so it's smooth enough to insert something into it. So there's going to have to be some consideration for the ID of the type, how true it is. And then, but I'm gonna kind of what I'm gonna model out here is kind of like a theoretically exact. So I'm just going to consider that my inside pipe is cleaned up and that it's right at this 2.067 diameter. And I'm going to build a part that fits into there, right at that theoretically exact size, and then I'll apply some tolerance on my prints to compensate. And and I'm gonna have to rely on my technicians that are gonna build for this to address some of those issues. But anyway, so there is a little give and take here, like these kind of applications where I'm working at here, and I'm thinking of a machinist gonna have to work this into a pipe. This is a good time if you have an in-house group, you have a conversation with them and say, is this going to be a problem this way? Or generally, an engineering group leader might already know the answer to this, and so you get some without even walking out to the technicians. They might already have the answers to this kind of a fit up in house in the engineering department or drafting. So I'm going to try to find some answers there, but I'm going to kind of model it like what's theoretically exact how it'll fit, and so I think this is too much clearance all the way around that. If I just purchase 2 inch solid bar, which is a real standard stock size, and had the machinist build this to fit, we would have some maybe excessive tolerance. So I'm going to take care of that and get materials that will be bigger. So my first thing that I decided, this was just kind of leftover residual thought from when I did this modeling the other day. I noticed this gap was quite, I thought, large. And so I knew I needed to take a look at this when I got back into it. And so my option is that I can either buy thicker pipe size and have it machined out because maybe the next size up, I don't know what it'd be, schedule 80. Maybe it's a lot more, and then it might be a lot more material, and which and the reason why I'm at 2 inches is because I've got a 2 inch bearing, and that's kind of the size that maybe the engineered design should have. So I don't want to start drastically reducing the size of this. I've already pulled my bearing that I'm going to use. It's a 2 inch bearing, and so um, not that I couldn't have it step down the shaft to fit into a smaller diameter and then step up to my drive size. I mean, that could be done, but I think I'll leave my Schedule 40 pipe and I'll just consider getting a larger section of rod, larger diameter. And so what we did is I brought up in our course, I did upload um, this manual here. I'll just show it back up. And we've reviewed it before, and this is something that's in this kind of industry, I would review a lot, and it would become one of my normal like reference pieces of material. Is like just what is normally stocked. Like these steel supplier handbooks can be handy. This is Pacific Steel, which is local. It's a local company here, and they're all over the Pacific Northwest. But there's one in Idaho Falls, one here in Pocatello. So this is a place I can just walk, down the street and pick up some steel. So I am going to. Sorry, let's see what I'm doing here. Maybe I'll need to say what it is. Maybe I'll never turn this on for other people to get to yet. But what I'm looking to get into is this Pacific Steel Handbook. I just want to show you that one of their categories will be solid rod and in the sizes that are available in that. So I've told you the 2 inch is definitely a standard size. So I'm just going to scroll down through here until I see that type of material. There's angle iron, and definitely this kind of stuff takes a while to learn, like what materials are available. But here's hot and cold drawn rounds, solid round, and so all these sizes are available. And actually, from anything under an inch and up to 2 inches, even 3 to 4, we have a ton of different size selection available on the shelf, essentially. And so I don't have to just buy a 2 inch one, although I know I need to get it down to 2 inch to drive on the bearing. But I could, so as a machining part, I would want to purchase something that's larger and machine down to it. Um, but then I don't want to purchase something that's way too large and make them do so much more machining to get it down to size that I need. And so, I'm going to try to pick something that it will give me the fit that I'm looking for, but it can be a machined fit. So something that I could, is a little bit larger, subtract down to it. So what I've decided while I was thinking is I'm gonna say I can purchase 2 1/8 inch rod. So it's bigger than two. Looks like it's on the shelf. One thing to note is additionally I would have to consider what material types. And I do think I'm in the mild steel section of their materials. And but it's general like most suppliers, uh well, I would say it's pretty common that these sizes would be available in stainless steel as well. They might not be available in all steels, but maybe mild steel and stainless steel, or a variation of some series of those two. Um, but Pacific Steel themselves, they do have a stainless steel section, like clear down towards the end. I don't know how far I have to get. They have structural beams, some other paneling, stairs, grip stairs. Yeah, they have all kinds of stuff. They do have, so here's some aluminum products. They don't carry that much aluminum product. And that's just our local supplier doesn't carry as much, but suppliers in different suppliers in Salt Lake, Seattle, Portland do have more sizing required or on hand um, of different material types. And so sometimes companies that are using these different materials get distribution from, yeah, sometimes local companies, sometimes they're coming out of Salt Lake around here anyway. Sometimes they're coming out of Seattle or Portland where they're on the shelf. I still might not have all the mild steel sizes might not be available in stainless, but I'm going to say I can get 2 1/8. Because I think down here past the aluminum, there's a little bit of stainless steel. And this is just because Pacific only probably stocks a relatively small amount of stainless steel. There's bigger distributors for sure for stainless out of Salt Lake. And and so they don't like if I was just thinking of the round bar that's available in stainless at Pacific, 2 is their max. So I would be looking maybe to an alternative supplier to get if I'm going to go bigger than this. And that's pretty common. So this is a little misleading, and this is the only sizes that would be available. This is the only sizes Pacific has on their shelf, probably. And but likely I can get some of those other mild steel sizes, whereas Pacific stocks a ton of different mild steel sizes, but not as many stainless. But the stainless will be manufactured in similar sizes of those sizes. Maybe not all though. That can still they are different materials, so they might cut some corners and only do eighths or quarters. And I don't know. I don't have it memorized. I'd have to refer to their catalogs, but I'm going to anticipate that I could source a 2 1/8 inch shaft, and then my machinist should be able to machine that down to the sizes that will fit nice and tight to the other materials I'm purchasing. So I'm saying, yeah, that's pipe. Sorry, the round bars there. I'm going to say that I could source some stainless steel shafting that would be 2 1/8. So what I did, so that made me change my part size a little bit, even though I'm following the standards in the conveyor manual. I'm kind of deviating from them here for my application. And so something that I can build. We'll just end my here. And so I want to make those adjustments. So I've already done this. I made a mistake, didn't record, of course. I do that frequently. This is my redo. Um, so what I did is I came back into, I think this part we only had a single extrusion of it. So really I'd be at the point where we should have left off from the last video. And I'm going to come in and edit this sketch and increase the size up to, that next source of material that I can get that will be bigger than what this is. So I'm going to say I need 2 1/8 inch round bar. And then of course that's too big. That is my intent here is that I'm planning on having to do less work on the pipe itself potentially to make this fit. And I'm going to have them actually just machine. The pipe is actually hard to handle for a machinist. This thing is, 8 foot plus long. So it's not like I can just put this in any, machinist lathe or something and be able to address this. So it's going to be easier for them to work with the shaft that's only, less than a foot long. And that's a better machine part. So this, I'm trying to make them do less work with the center pipe. And so now I've got interference in the shaft in the center pipe ID here. So what I'm going to do is I'm going to come in and now the only part that this is interfering with is with the part of my shaft that slips into the pipe. And so I'm going to come out and do a sketch and subtract this amount of material from my shaft. Because my shaft I bought is 1 1/8 inch. I'm just going to tell the machinist, come in here 4 3/4 of an inch and machine that down to this bore size here. And then I have, I've eliminated the interference in my model and I'm sourcing material that will help the machinist do kind of a subtractive machining process. So starting with something big, whittling it down to what fits. That's a good thing. And there could be a standard at companies of how much they want you to go over or how close they want you to be. The machinists are going to have their preferences for sure. How much material you give them to make things straight and true. When raw material is delivered, it's controlled, but it's still like a machinist is going to get in and true things up. So even if I needed this, even if 2 inch would have worked for me, the problem with sourcing 2 inch material for this kind of 2 inch shaft is that the machinist might not be able to take off enough material to true up the surfaces that go through the bearing, which is the most critical surfaces here. And so, because there could be some deformation, even though it passes inspections to be 2 inch round bar, uh, and it might slightly be over even in that, a tolerance definitely in their raw material sizes. But a machinist is not going to love to source some 2 inch bar to do a 2 inch bearing surface. They're going to want to machine down to 2 inches and have enough material to make that super straight and true and totally controlled. And so they may even want more than an eighth of an inch. And so, that's something that generally engineering design groups, this is another thing that they would be well aware working with machinists of what the machinist might require. Maybe they want a 1/4 inch of material, but you don't want to get a 1 inch bigger because then that just makes them subtract so much more material. So there is this range that is going to be specific. So anyway, I'm giving them an eighth of an inch, at least giving them some material. And now I'm going to go cut. So I'm going to say it is. That's 2 1/8 now, so it technically doesn't fit. Back to my end. So now it doesn't fit in there. So what I'm going to come in here and use this, my derived part end face here as a sketch point. So I'm just going to say, come into here, let's do a new sketch. And what I'm going to do is I'm going to project what needs to be sliced off of from here to the end of the center part to make it fit inside it. So what I want to project is on my sketch plane is I want to project definitely the outside surface of this. So that's the overall. And then I want to project the ID of the pipe. You might be able to get it here, or this could be kind of annoying to get to know where is the ID of the pipe. Like I even could come clear over to here. This is the ID of the pipe. I could project it from there. I can get to it easier, or I can try to deselect some stuff here. I'll exit my sketch and turn some stuff off to get that. But what I'd be looking for is I've got these two projected. It will create a closed that I can just shave down 2 1/8 inch shaft to fit inside this theoretically correct ID of the pipe. That's what I'm going to do is finish and then just do an extrude cut here. Cutting. I'm gonna look for my sketch to show up. So this will show up. I just have it right there. I'm cutting. I'm not going to cut that way. I haven't addressed this end yet. I'm just addressing what goes into the pipe. So it is directional specific. I want to go just this way, cutting my shaft to fit inside the pipe. That much is going to be cut and machined up. So this would be how far do I want to go? I'll just say like through all that direction in case I ever change this dimension. They only want to go this direction. This has not been cut from here. So I'm gonna say okay on that. Now when I do my little section view here, intersect. Now I've got kind of a theoretically exact fit, which still isn't what we want, but we'll take care of that dimensioning on our drawings and give them a tolerance for what we think will fit, and that might have to be discussed. Or have to have the pipe on hand to take a look at how rough the inside is and what's going to happen to make this relationship happen. Going slide it to the machine finish, sliding into potentially a rough finish. So still would be some work to address this, but at least right now my model's kind of theoretically. So we'll say, take a look at that. I've done that. That will update when I jump over to oh, I can just turn off this surface for a little bit and just see this is what I've done, right? I've just cut that down to fit inside it. All right, so now that's one end of it. The other end is the bearing end. So let's address that. So I'm gonna jump over to this, go ahead and update the assembly here. Now that should be fitting in there. Exactly. And you can't tell because this surface over here is bigger now, but yeah, it fits right in there. And then but at this stage, this is the next one out where both the screw and the housing are in an assembly together. What we need to do is I'm going to bring in the bearing. We've already got the part file created. It's the driven bearing, the smaller one. It's bigger in some ways. It's got a bigger footprint, bigger bolt pattern, bigger bolts, but it actually is kind of a smaller profile this way. This bearing I need to bring in. So I'm going to bring that in and just kind of evaluate it with this shaft and then come up with some ideas and some dimensions to modify the shaft to meet that bearing. So I'm going to go search for that and place it into this assembly. Oh yeah, place my part. Should be in my parts folder. I don't know what it looks. I can't remember what we named it. It was pretty early on when we were working. Actually, it was one of the couple first parts. We pulled these bearings pretty early. This one is the larger one. Larger this way. It's a thrust bearing, different kind of bearing assembly inside of it. And then this one is the driven bearing. So this is the one I'm going to pull in. Your model might look similar and say, okay, I'm just going to place it in here. This is the bearing that goes on there. This is the 2 inch. This is a 2 inch bearing. And I'm going to open up the data sheet on this uh, in just a minute. First, I'm just going to go ahead and constrain this in on this shaft here. So I'll just say constrain um, the axis of the bearing here onto the axis of my shaft here. Let's just do that. Those are the two parts that are fitting together. I'll apply that constraint. And then um, we actually had an industry partner in here this week that passed around a seal plate because they build this kind of equipment. And they have a plate. So what I'm going to do is normally I would come in here probably and just like constrain this face to that face. And there could be a lot of assemblies where that is an adequate relationship. For this particular industry, we're going to actually pull it away and create a seal between this bearing and the materials that are inside the um, the screw conveyor that might try to leak out, even just water trying to get out of here or whatever it is, can get through the end plate. And so there would be nothing preventing that from happening. You know, it might be minimal, but over time it can be a lot. And any water coming through here into my bearing is, you know, water and bearings. They don't love that. They like bearings like grease. And so, and so we want to protect the bearing is what we're trying to do with the seal plate. So we actually, you know, we're going to create another part in this assembly, and it's going to be sandwiched between the outside of this housing and the inside of this bearing face. And it'll be to protect and to actually it protects it both ways. It protects, you know, stuff from outside getting in and inside getting out. So it kind of acts as good for both directions of stuff. You don't want, you know, I don't want stuff going in and out of this at all. So um yeah. And so how I'm going to constrain that. So I've got it on the shaft, and then I just want to do a face to face. So I'm just using the bearing face against this face. And this is where I'm going to add a 1/2 inch. So the plate that we're going to assemble here later is going to be a 1/2 inch plate. And so I'm going to say, okay, let's keep it a 1/2 inch away like that. And we'll insert a seal in there another time. And then I have so all this does is just rotate around. So I'm going to lock this in. I mean, this thing is technically just a bearing, so it's really uniform and symmetrical, but it does have a grease zerk location, and these become kind of important just because you need to be able to access this to apply some new grease in this occasionally. There are greaseless bearings that are already sealed and they are designed not to accept any more grease. But if they do have a grease zerk, you'd want to put it where somebody could get to it. And that might matter where there's decking or there's an access point. It can plumb these lines in, like use some tubing and a place that a person can access. And then so it's just kind of like plumbed to a access point where they insert grease and just because you can push grease through piping like anything, so they can actually hard line these grease in, or it might have to be accessed. I'm just going to put it at 12 o'clock position. That'll be my last constraint here. It's just something like I'm on my part, and I'm looking at my sorry, it's hard to see, but I'm on my origin of my part, and I'm looking for a plane. It is I can check this before I even get in. Looking for a plane, one of these planes here for this part, like that one. If I can just do a plane to plane constraint, it'll constrain that into the 12 o'clock position. And I could always rotate it if I need to later. And so that plane is XZ on the part. And then I'm going to go clear up to the origin of the assembly and look at what plane would match with that. It's like YZ is in the same orientation. So I'll just say, yeah, constrain YZ to my XZ plane like that. And it looks like the initial selection threw it to the bottom. So I'll choose this one. My grease circuit 12 o'clock. So I'll say, okay. And that thing is constrained. I can work off it now. So now that's where it's going to really live. I think when this assembly is finally done with the seal plate in between, the bolting hardware that's necessary to keep it there, that's going to be the position it's going to be at. With my auger in the correct position, it's 1 inch in the end plate. 1/2 inch in the Let's start here to this to the end of the center pipe. That's 1 inch. So that's just kind of following my manual. And so this is definitely going to be, my overall length. This is a problem though. Having this much excessive shaft coming through a bearing is really an OSHA violation. So it's definitely a safety violation. Just because that thing will be continuously rotating. If this is going to be running 24/7, pushing the whole potato down through here constantly, you would not want this to be anywhere near anyone sitting there spinning, catch your clothing or whatever. This is super dangerous. So, what we like to do is, and this is probably a standard, or this is something that I know, but I'm going to bring the end of this shaft in to where it comes through the bearing by 1/8 of an inch, and then it terminates. So it's drastically reduced the danger of being able to catch in it. It still needs to come through the bearing, surface completely, and be proud of it. And so I'm gonna choose the dimension of 1/8 of an inch past. And so what I'm gonna do is just take a quick measurement. Now that my bearing's in place and my shaft's in place, I can just say, well, this has to go to here, but I only want it to be 1/8 of an inch. So I've got 2.961. And so I'm just going to say I need to reduce that to where it's only 1/8 of an inch. So I can just take my calculator up here, right? And I can just say this is my current situation is 2.961. I need to get it down to 1/8 of an inch. So I'll just subtract 1/8 of an inch from it, 0.125. And then this is how much I need to take off this shaft to get it to where it's only 1/8 of an inch. So let's say I need to go into my shaft extrusion and change this dimension by this much, 2.836. So jump over to my shaft. No, I'm actually in the right one. I should say done for a minute. Jump over to my shaft that I was cutting the inside out. Now I'll start cutting the outside. I'm just going to at least cut it down in overall length. And so that's actually the first extrusion that we did. So I'll just go to edit it. And we did a asymmetrical extrusion here. The part that goes inside is 4 3/4. The part that is coming out away from the center pipe is 7 1/4. So I can just do an equation here and say, that was from the manual, but technically my parts fit up this way. They're like 2.3 6 on my. I have it. It's 2.836. 2.836. I'm just subtracting that from my original dimension that I established. This is probably not a great use of an equation because this doesn't really make a lot of sense. But so I'd probably come in and like change this to just a solid dimension. Anyway, it'll drive it that way. But I'm going to say, okay, subtract that much off of it. Now I'll just go take a look at how this affects mostly at the, I won't really notice too much here. But I'll notice it in this assembly. So I just hit the update. It actually really accepts the update. That is a safer OSHA standard there, just coming through the bearing. And then we would we'll go do some refinement on this now. I do have an interference problem here, right? It's 2 1/8, and I can see that through a section view now. The bearing's in place. I'm just sectioning through here. Here's my set this for a minute. Yeah, here's my, which is a good thing because I've got this part upsized so I can machine down to fit this bearing really true. And so I want to know what to cut this down. So what I'm going to do is take a quick look at the specs for the bearing, the resources that came with it. So I just go over my file browser. I've got mine saved in my resources folder that I built, and there's the 2 bearing resources that we have: the roller bearing, the shaft mount ball bearing. This I think is the bearing that I'm looking at here in my assembly. And so this is the data sheet that was pulled from McMaster Carr with it. So what it has is its overall dimensions. I'm just kind of using the model to represent this, so I've got it placed correctly. And this is where we picked up our hole pattern in the end plate. But this is also what it says is, it is for shaft diameter 2 inch. And so this is their bearing dimension they have. So you're going to get supplied a bearing that's 2 inches. It could be up to 0.2 thousandths. I mean, it's a small number. This is 2 10,000ths that it could be over, and up to 8 10,000ths. Is that right? Yeah. 10,000ths, yes. So, which we're not even to the thousands. So this is quite tight tolerance here, 4 decimal place tolerance. I'm going to model mine in a 2 inch shaft. Well, I'm going to cut mine down to 2 inch. And then I'm gonna have to consider my drawing and what kind of allowance I have here. So it does definitely have to fit in here. If I can probably maintain, you know, 2 inch plus or minus a couple thousandths, I'm gonna be, or I don't know. I have to think about this, but I definitely don't want to exceed this at all. Because that's what I'm going to be supplied. In fact, I really shouldn't exceed the lowest value here in case it is that small. And I've got, that might be the smallest value here would be the one that I really want to probably design around. So I'm going to cut mine down to 2 inch. So you come back into here and cut that down. It probably will look like it like fits like size on size when I cut this again. But let me turn that on. And let's do that. Let's cut on that shaft. So I'm going to come here and I'll do it from the same. I'm going to turn back on my surface. I'm going to do another sketch. I'm just going to do this as a separate step. I'm going to say, I'm going to start my 2D sketch on that same face though. And that's where I want it to be, just right there. And what I'm going to do is I'm going to project the outside 2 1/8 inch dimension. And I'll just go F7, slice the graphics. I'm just going to draw the size that I want it to be finished, just to towards the bid. So now I've created this little cut, yeah, it's actually bigger than the ID cut. I'm actually going to become smaller than the ID that I just cut on the bearing side of things because I'm cutting that whole 1/8 inch off to get it down to 2 inches. So I'm going to go ahead and cut this profile. So that's all I need is a 2 inch projected of the actual end of this, the largest size, 2 1/8 projected that. And then I also do a 2 inch circle. So I'm going to say finish that. I'm going to do another cut to that shaft of that profile that I should be able to pick up right there, that profile. And I do want it to go that way now. So it's going the correct direction. So I'm cutting this down to be just 2 inch in diameter. And so I'm not going to pick that. I'm just going to say through all. And that is the correct direction. Don't cut that way. I'm going to cut towards the. I'm going to say okay on that. And then I'll take another look at this before I leave it. But then what I really end up having is that's been machined down to fit in the pipe. This has been machined down to fit in the bearing. We started with 2 1/8. Actually, we whittled it down in both directions, but the smallest size is the bearing side of it. So I've got this little step in the shaft here. So we can look at that in this. I'll just jump to this quick assembly here and hit it. Now, yeah, this is fitting into our bearing. Have that I don't have that interference that I was seeing between the two sections of material there. And this is theoretically kind of exact. And then from here, we might have to apply some tolerance. We'll find out, yeah, apply some tolerance on our drawings, detail that out. So that's all I want to see is that to continue that. No, that's okay. We'll just say that's the end. But there's a couple little machine things they'll do here when they have this going on. And one is they don't love to leave these edges here, just like a sharp edge. So the machinists generally they'll just cut, just kind of do a flat cut on the edge, a chamfer maybe. So we're going to add a chamfer to this edge. And I'll add the same chamfer to the inside edge that's in the pipe just because it'll help like instead of being a sharp edge corner there to go into the pipe, we'll go ahead and have the machinist put a chamfer on both edges. So the one can go in and the other one is a nice finish outside the bearing. And I don't think I'll do an 1/8 inch chamfer, but I'll probably do like a 16th of an inch chamfer, just about half this distance out of the bearing will be just chamfered off. So I'll do the same on the other end. And then I'll address this little shoulder that's now in my shaft. In some cases that is a machine finished and there would be some design for that. In this particular case, this is really just out in what I call like, in nowhere. Doesn't really impact fit at all. And it doesn't need to be a sharp shouldered edge like this. It just doesn't go up against anything. So what I'm going to put in my model is a fillet here. I'm just going to fillet from this edge and just have it blend into the actual shaft as it turns down to 2 inch. So I'll just have them put a fillet here rather than a sharp shoulder It's not really required for my application. Yeah. And when it's not required, I think machinists and I prefer to just have a nice contour there of change from one shoulder height to the other. So I'm going to put in, so I'm going to do a couple of just detail finishes here. So I think I'll do my chamfer is easy to do. I can do my chamfer command, and I'm just going to set the distance. I don't need an 1/8 inch. It's kind of large for this application, but even just a 16. 0625 is a 16. I'm going to say let's chamfer that edge. Let's take it off on that finished edge, and then take it off where it goes into the pipe. And that can even be more on the send if it helps, but I think that's a good start. So I'll say okay on that. Got my two ends chamfered, and then let's do a fillet. And I'm gonna pick a specific height to fillet. I just want it to be once this diameter is reached, just from that down to here. I'm just gonna do that fillet size, the difference of these two. I don't know what that is. I'll run my calculator again. So this measurement is what inside of the pipe 2.067, and this is 2 inch. I think I actually did that calculation. Probably in my history. 2.067 minus 2. Yeah, it's the difference is like kind of 0.67 in diameter difference. And so really this is like half of that distance. So it would be that this is going to be my fillet size here. That's the distance in diameter, the difference in diameter all the way around. And so I'll say I'm going to make my fillet size 0.335. I'm going to come in here and fillet size 0.0335, just a little bit bigger than 32nd. It's quite small. And I just need to select the edges. So I'm just going to select this inside corner and have it do this little concave kind of fillet transition between the two shafts. So rather than a convex one like a weld might be, this is going to just be scooped out. It actually increases just a little bit more material there than a hard shoulder does. And smoothie transition. There's some weight distribute or some probably some distribution properties going here of anyway, yeah, of forces that they're impacting this a little bit. But yeah, I just look at it as almost like a detail that's more just a smoother transition between these two changes. So then it ends up with maybe a finished shaft, something like this. Slight fillet, chamfered on both ends. Go ahead and update my assembly here. And that is that. So I feel like I'm happier with this overall profile of how all those parts are working together. And now I just have to worry about how they actually do work together. This is the relationship that bearing has to that. It just slips through the end plate, doesn't contact the end plate. It's freely, and then this is what supports it. And I need some hardware to hold up the bearing and a seal plate between the two. So I've got some work to do between, mounting the bearing. But then they would just instead of having the bearing slip instead of having the relationship of where you don't want this to slip in the bearing, so you have these set screws that will drive down in and bite against this shaft, and so that instead of the shaft rolling in the bearing, it's actually the bearing roller balls in here that would leave it twisting for us. And these two will stay locked together in rotation. So, all right, that's how that works. And but let me go back to the screw itself and look at this relationship. This is how it's really going to be built before it goes into the housing. And then they're going to want to pin these two together. So our manual, I think I have the manual still up. I came across this, it doesn't have the exact drive and end shaft, maybe dimensions for how to make configuration, bolt them together, but it does have like the couplings, so this does apply to end shaft detail here. And what they give me is that what's going to go on is that yes, I could drill through the pipe and through the solid shaft, and then use a fastener like a bolt and a nut to make that connection so that the shaft doesn't spin in the center pipe. I need to lock those two together. So this is one way to do it. We're going to do a welded, like a more permanent, but still actually is you could actually remove the weld and still disassemble it. Just not as easy as taking the bolt off. You have to drill out the weld, but that's pretty common for screw out repair with. and for it to have new drive and driven shafts rebuilt on an auger. Sometimes the bearing, fell apart, the bearing and the shaft rubbed together, and now the only thing that's ruined on my auger is just the drive shaft. Well, then we replace that and we continue using what's good. And so this is designed to be maintained. And so, but I'm just not going to use a bolt, but I'm going to use the dimension they're giving me. So I'm going to say on my end shaft as it goes in, they're giving me the C dimension. First off, let's say what you would use. So if I'm just looking at, well, how big is like a bolt or a pin going to be to go to hook these together? And they're saying on shaft diameters up to 2 inch, uh, they would use a 5/8. What's this for me? I may have done the 200 pounds because maybe I read through fast and never stopped. I may have looked at pipe size and bolts. I should have looked at shaft diameters too. Pipe size 2.5. So this is my redo. In class, I'm gonna make people fix this, but should have been a 5/8 piece of 5/8 hardware, and is gonna go through to bolt it together. So I've got to make a hole big enough that a 5/8 bolt could fall through it. And so it's 5/8 in diameter, and then I'm not going to use a bolt. I just want to use the diameter of the bolt for my reference. And then I'm going to make it these other dimensions. I just want to know how far from like where it comes out of the center pipe, how far back do I pick a hole, put a bolt or a pin through here. And they're telling me that that's that C dimension. And so C down here, shaft size of 2 inch is 7/8. But 7/8 away from where it exits the center pipe. I'm going to put this hole in, and then and then it has an E dimension for how far it is maybe off when it's inside the pipe. Because what we do is we actually put two bolts in, and they are 90 degrees from each other. So it kind of shows that assembly. Actually pin it in one direction and then pin it in the other direction. And that is essentially it's taking the torque of these two and trying to twist that separately from each other. A lot of that load's going to be on these things. So take that torque, not and then to spin them together. So this is kind of critical to have these two of the 90-degree angles from each other, and then they're in on my that I'm not too close to the end of the shaft, but then also set that. And so I think the E dimension of them being the same for 2 inch. So, yeah, E and C are the same. So I'm going to use those two dimensions, put holes in my assembly. You're big enough for a 5/8. I'm going to jump over here. So it's kind of a little bit technical. And what I need to establish here is maybe I'm just going to take a good look at my auger here. And here's his back and mine's front. That's okay. In my video I made yesterday, I made it so it actually was oriented correctly. And we did it together in class. I think what we did different is we put the flights starting on the opposite end of the shaft. That's the only difference. It really doesn't make that big a difference with the shaft symmetrical. So it's just a slight orientation thing like I didn't do correct in class that I corrected when I did this. So yours might sync back and that says front, but it is the in-feed side of my conveyor where the flights go all the way to the end, and that's where that shaft should be. And that matters. I'm just going to do some work to pin these together now. And so what we do is this assembly stage. I think it's for somebody done like just sketching and assembly, unless you've done some of it yourself. But I don't think I've done it on the side. You can just do you have control. You can do a sketch in here and impact these parts at this level. And so what I'm going to do is I'm just going to orient myself so that where 12 o'clock is maybe. And I want to be a sketch. So there's a couple ways I could do this. Maybe I'll just do it the way that was most successful. We kind of do it two ways in class when messing around, but I think the way that was most successful for me was yeah, show you like I don't know. I'm going to establish some work. Let's do this. Before I even do a sketch, I need to establish what I want to sketch and it's assembly to draw down through. So I'm going to establish a work plane that's tangent to this kind of parallel to one of the origins. So if I say the first hole I think I'm going to draw is going to be right here. It's going to go through this way. through these two parts. And so I'm going to make a plane that is tangent to a surface parallel to plane. And you could choose either one first. I am watching my command line lower left, and it says select curve or the planar face. I'm going to say it's tangent to this surface. And then now I want to pick the next, it's got to be a plane next. And I'm going to say I want it to be tangent to that and parallel to whatever plane this is, YZ, the one that runs vertical through here. There's YZ plane. I'm just looking at it. That's the YZ plane. So YZ, that plane. So what it's done is built me a working plane that's tangent to my center pipe. Even if this pipe size change, this plane is still maintains tangent to that pipe, that surface, and then parallel to that plane. So now I'm going to be able to do a sketch right here, and I'll be able to cut through these two points together. This is, so I'm going to do a sketch on it. Could have established it on either side. It wouldn't matter which side of this sketch. It really does. So whichever way the I just use default, whichever side it put the point on. It was fine for things. I would pick this side, no difference for what I'm doing it with it now. So what I want to know is my dimension, my hole was 7/8 over here, and then kind of centered through here. So what I'm going to say is I'm going to project the geometry of the end of this chip. Either one here, but really I'm just this outside band, and it's going to put a line. So it's my hole needs to be 7/8 away from that. So I'm just going to offset this line 875 to 875, like 7/8. And so now I've built my line. It's that's it was for the center of the board to be this way, and then in this direction. I just need a reference point there as well. And so I'm just going to this X Z plane. I project the XZ plane. It gives me a crosshair from the stone. See this, so for some it worked. If they did this maybe, and they placed the point here on this intersection point, make sure it's constrained. Sometimes I might just like place it on this line constrained, and then it would still move up and down, and so I can just be a convincing constraint. This line. Now I know it's hard to see though, but I know that point is constrained. I can also do a circle that point and do this to be big enough for the fastener. It's a 5/8. See, it's 0.625. That's the we put a half-inch fastener in the class. 5/8 is actually close. However, that would be like a size on size, and in this case, it is just a bolting configuration. So I need to have it a little bit bigger than that. 30,000 is not what I need to. I can check the. I did this in class. I checked. So what I'll do is I say these are my two sketch items. I have a point and a screw the circle. So I wouldn't necessarily do both always, but I'm going to kind of use one strategically. And in my whole command, I could go to this. This was my original thought. I'd use the whole command. It's kind of how we develop our other clearance type holes. It's one of the options in the whole command clearance layer. With really no seat, just a square flat finish, and like cut through all. And yeah, except for mine was acting not calling like opportunities, showing up going both directions. Maybe somebody said they could, or maybe I go this way. Maybe it's this direction through all, but I might not know what through all is for me. So mine's not picking up like it can recognize both of these parts. And so I kind of like, I could say two next and come to the surface and kind of come through and put this hole in it. It'd be a brief hole for a like a hex head bolt, which you normally go through here, maybe 5 or 18 diameter. And really that's going to put a through hole that's like 656 in diameter through there. So with that 5/8 faster, we have a little bit of tolerance, still a little bit easy. So I could use this as information to say, I think I'm going to use, if I was to put a clearance hole through here at 6x6, And this might work. Let me hit OK. Mine had an error. Some people's didn't. And so where mine had an error, I just kind of used it as informative instead of. I just increased my 0.625 polygon over here, super. 656. That would be it would be kind of the same size that I could get the whole thing. So this just kind of didn't work for me. I could say, well, cancel that. Um, and I could just probably spend some more time with that and see, like, do I need to make a selection of the parts before I do that hook command? But I could also just do a clean cut. It's just that I want that to be 6 by 6. So I might edit this dimension. But everything I'm not really doing 6. It's like, yeah, it allows me to edit that, even not going into this. Maybe that's something that I haven't done it before. What a new function. 656. I could be wrong. And now I want to do an extrude on this. So rather, if my whole command didn't work, I can just do an extrude cut. I think this is going to recognize just a cut based off what I've got going on here. And I'm going to say the other direction. And I think I can say through all. That recognizes the flight as a part here that we want to cut through too. You can say maybe two next, and this surface is the two next. That might not function right either. I'm going to say through all. And even if this is cutting through too much stuff, mine actually misses my flights just by the way I've oriented it. But um, I happen to then need to move my flight orientation, and it cuts that this cut is going on. It's cutting through my flight. You can unselect it from what's getting cut. And so I'm just going to say that through all right now, and that's actually going to produce a hole kind of above your actual assembly. It ends up being right below your origin point. This extrusion got done in the assembly, and it's like cutting both these parts. In fact, I think if I bounce out to this part here, at the part level, it's not accepting that it knows that this is done. So really, the machinist is just um, doing this work, and then it's going to be inserted into the end of the center pipe. And then once that gets inserted, they're going to maybe bring it back into a lathe or a mill or something, and go ahead and perform this cut through both of these together to pin them together. And so they're going to have kind of an order of operation sequence in order to put this thing together right. So I've decided to do my cut here at the assembly level, kind of like it's going to be manufactured this way. They're not going to machine those holes for the pins probably until they're inserted into the center pipe. Otherwise, you have to be worried about hitting those holes, but you can't see them because they've been drilled in the shaft first, so you don't know where they are without doing some layout work. And so maybe it's easier for them to drill the hole all through the thing together as an assembly. And but different machinists can do things different ways. So you have to kind of be ready for that. This is the way I'm going to do it. And now I'm going to do the same hole, um, 90 degrees from that. So I'm going to build another, this plane is the one I just used. I'm just going to turn it off. And now I'm going to do another, I'm going to establish another plane tangent to a surface parallel to the plane. I'm going to say I want it to be tangent to this surface again. I want it to be parallel to a different plane here. I want it to be parallel to this plane, the XZ plane, right? I'm going to say XZ. Yeah, so it's tangent. I don't care if it's top or bottom here either, actually. So mine is jumped to the 12 o'clock position here. And so I'm going to do the same sketch. I'm going to do a set sketch here. A new sketch. What I'm going to do is project the end of the shaft that's on the inside of the pipe. So you can select it from here. You can't see it, obviously, but I can run over my model and see the edges that I have selection. Some of these are flight edges. If I zoom in here a little bit, I know about where my end shaft ends. I probably see it. There it is. It shows up as, I mean, that's the only other thing that's on the inside here and I'm getting two different diameters because I put a chamfer on it. So it actually has the very end of the shaft is this little smaller circle, and then this one is definitely the bigger of the chamfer here. So I'm gonna actually choose this one, and if that confuses you, you could actually go out of the sketch for a minute and turn the visibility off, or turn the view to a wireframe. Does it make it? You can do that within a sketch. That's kind of handy. There is the end of that. I just kind of know what I'm looking for, so I'm kind of scrolling across here until I see the shapes I'm looking for. And this is the one we want to project. I'm gonna project that. And now I'll just jump back to shape. That's the end shaft. I need to offset that. This way. 875.875. And then I'm going to also project the intersecting plane. It would be coming through here this way. So that's kind of like the YZ plane, YZ. Right there. And that's the center point there. So I really don't, I'm probably going to do just a circle extrusion on this sketch here. It's the 1656. I could be, I think that's what I'm thinking is correct. But I'm going to change both of these dimensions. I'm just going to have them driven by the dimensions from this sketch rather than be the same dimensions. I actually want them to always be the same. And if I have to get into both features and change that, it's a little bit, I can forget to do one maybe. Um, oh yeah, I'll go up here and I'll kind of look through my list. It's just kind of like keeping a number sequence to the dimensions I add. So these are the last two ones I just added. Technically here is the first two ones that I added. So really my 875 dimension is D29. So I can just say, oh, this 875 dimension that I added twice, I could just drive it and I'm changing it to D lowercase D29. That's what it is on the spreadsheet above it. Yeah. So instead of being another unique dimension, it's just if I change this dimension, that one's going to change. And then I'm going to do the same thing with D36. I want it to be this one right here, D30. So I'll just say this is actually D. And then I've just simplified my sketches there. This is pretty common to do once you get into design or into trying to reduce variables or reduce errors through so many sketches and things that could be related. We can get them related, and so this is maybe and there might be more refinements I would do, and I could refine the dimension name to actually be a name. It's identifiable, and so there's a lot of work someone can do in here to define the variables. So I'm just going to say done with that. Now those are just driven dimensions from this first sketch here. And I'm going to say finish that up now. And I'll just say cut through there, right? Yeah, I want to extrude cut this. I could have turned on some construction lines because I have a full profile. But that'll work. We cut it through all in this direction though. You say, okay, now I've got two holes cut through. Yes, I'm going to turn off that work plane that I just used. And so there we go. That's actually how that assembly would be prepped and ready for now. This is where we got to class. This is where I ended. Is just that now I'm ready to actually build a pin that goes through here to actually, and I'll build just a separate part that slips into here. What I said in class is I decided I would make it long enough that it comes up about halfway through this material and about halfway, because what it's going to become is plug welded in. So I actually I bring the part up in to somewhere below the surface. And in this case, this is about, I don't know how thick this wall is, not a quarter of an inch thick. But in this case, it would be nice, about halfway through into that surface, leave a little bit of a cavity to kind of fill up with weld material. And they'll probably weld it up to where it's a little bit convex when they're done. So it's like kind of a fully filled hole. If I had a really thick piece of center pipe, maybe it's ½ inch plus thick, I still would probably bring that in maybe further beyond than halfway, you know, um, surface from the surface to where that pin might be. If it's 3/8 of an inch, that's quite a deep little hole to kind of fill up with weld wire. 1/4 inch. There might be a standard here. It would be worth checking into. But definitely, I'm just going to bring it through about halfway on this too. So I'm going to build that part later. That's all I want to do today. We concept it here. Check this out on the check this out at the assembly level, and we'll see some pins in there eventually. And that'll be how that we transfer. This is really the driven end, so it's just how we maintain straightness through a bearing here. Bearing's going to do all the work for us. Pins are going to transfer the torque from one part to the other. Yes. Let's save this and that's it.